Hello, everybody. Welcome to this talk. Thank you so much for being here. I really appreciate you take the time on a Saturday. I know there's probably other places where you would rather want to be together with your family at home. Instead, you're here, stuck with me. I really appreciate you doing that. What I want to talk about in the coming 45 minutes or so is how to build a real-time data streaming pipeline from an operational database such as Postgres to a full-text search index such as OpenSearch. And I will talk on a few components and systems like those databases, Postgres, OpenSearch, but also tools which help us with doing that, like Debezium for change data capture, Apache Flink, and some more. So what you will find out more about is, first of all, I want to talk about a process, a technique which is called change data capture. And in particular, I would like to talk about one particular tool which implements change data capture, which is called Debezium. Then I will touch a little bit on stream processing with Apache Flink. And finally, I will, if the demo gods are with me, I will show you how to do all this in action in a live demo. A few words about myself. I work as a software engineer at a company called Decodable. What we do there is we build a platform for real-time stream processing and data movement. Essentially, the use case which I'm going to talk about today, this is something you could implement, build as a fully managed service on Decodable. Before that, I used to work at Red Hat, where I led the Debezium project. A few other things, you can see it all here. Earlier this year, I'm curious, has anybody heard about the 1 billion row challenge? A few people? Right, so this was a little challenge I did earlier this year for Java folks to be, curious about Java performance. Okay, so then let's talk a little bit about this real-time data pipeline. And imagine you wouldn't be here, instead you would be maybe in your day job and you would have this task. For our product, we need full-text search functionality on our data. Now, databases like Postgres or MySQL, they might have some search capabilities, but typically you would rather want to use a dedicated system for that, something like Elasticsearch or OpenSearch. Why? Well, because those dedicated search systems, they have just much more functionality for that, right? So they can do things like proximity search, fuzzy search, they can highlight your results. So essentially, if you wanted to build something like the Google search based on your own data, you would rather look at those kinds of systems. Now, of course, the question is, well, your actual data, your products, your customers, or whatever your application concerns itself with, this sits in this database, right? Like Postgres, MySQL, and so on. The question is, how do you get this data from this database over into the search index? And now, well, you could first of all think about a basic approach, something where your application would just do those two operations at once. It would write to the database, commit its transactions there, and then at the same time it could send a request over to the search index. And while this might work on the surface, it's not really something I would recommend because it's very unreliable and error prone. So for instance, just think about failure cases. So maybe your database transaction gets committed, but then for whatever reason there's a network split and you cannot update the data in the search index. So you would end up with an inconsistent state, right? So you have your operational database updated, but if you were to do search queries against the search index, it would show you incomplete results because you couldn't update the data there. Or it could also happen the other way around. You might update the search index, but not the database. Or there could be just inconsistencies. It might happen you apply those operations in different orders. Let's say you do multiple writes to one particular purchase order in a close, timely proximity. And it could happen you do change A before B in the database, but then B before A in the search index. And again, your overall system state would be inconsistent, your search results would be off. So this is, what's called dual writes, trying to update those resources which are not sharing transactional semantics, like a distributed transaction. We don't have that here, and it's just something which you shouldn't do. So then, what else could we do? And this is where this tool, Debezium, comes into the picture, and also the idea of change data capture. So let me ask you, who has heard about Debezium? Okay, I would say, yeah, maybe like 1/4 of you. Who is using it in production? Few brave people, very good, all right. So, to bring everybody onto the same page, what is the idea there? Well, we need essentially a source for changes as they get applied in our transactional database. And if we can then ingest this stream of changes, we could take those events and send them to OpenSearch or any kinds of consumers, really. So that's the idea. And this is how it looks like on a high-level picture. So all the databases, they have what's called the transaction log. The transaction log, it's an append-only data structure where whenever an insert, or an update, or a delete, or any kind of data change gets applied, this will be appended to this transaction log. And this is exactly the source of truth, you could say, for your database. And now what change data capture is about, and in particular log-based change data capture as well, it taps into this transaction log, extracts those change events, and then propagates them to the outside world. And well, what we could then, for instance, do with those change events is we could apply them one by one to a search index. And we would have the same state of data as we have in our operational database, also in the search index. And now this avoids all those issues of dual writes, because we only need our database for our application to write to. The application itself never writes directly to the search index, which means if we cannot reach it, it doesn't matter. We just need our database. Also, this ordering concern, if we go and extract changes from a transaction log, this is exactly the correct order of data operations as they were applied in a database. If we can get hold of that, we can apply them to the search index, and our overall system state is eventually consistent. So all this happens asynchronously, but eventually the data will be consistent. So that's log-based change data capture, getting change events out of a database's transaction log. And now there's a few tools which help you with doing that. The one I used to work on, the one I'm familiar with, is called Debezium. So it's an open source Apache v2 licensed project for change data capture. And it's an entire platform which deals with all kinds of concerns around CDC, change data capture for short. There are things like doing backfills of initial backfills of data. You could do things like filtering your data. There's a UI and many more things. I could talk for hours about the features, but keep in mind, Debezium, open source, log-based change data capture. And there's what I'm most excited about, I would say, is there's a very active and healthy community around it. So there's hundreds of people who have worked on that. So why is this so interesting? Why I think is this such a powerful tool? Well, it just enables a ton of use cases. So in a nutshell, it's like the observer pattern for your data, right? So whenever something in your database changes, you will be notified about it. You can react to those changes in real time, by the way, so which means low latency. It could be milliseconds, tens of milliseconds maybe, until you have your data from a database, for instance, into Kafka. So there's a tons of use cases. By the way, I wrote a blog post about some of the use cases. You can take this QR code and read about it. But really, for instance, you could use CDC for just replicating your data into something like a data warehouse or Snowflake or data lake. Or a search index, which is the use case I'm going to talk about today. People use CDC for updating caches. So maybe you would like to denormalize your data and put it into a cache close to your users, some sort of CQRS architecture. So that's also something you could do. You can use it for synchronizing data between microservices and many more. But today I would like to talk about search index updates and also how we can go about denormalizing our data. So creating data representations which are geared, which are optimized for particular use cases. Now, there's one challenge, and this is, all databases have a transaction log, but they all have different formats and different ways how you would access this transaction log. So there's not one standard API like JDBC, which would allow you to implement log-based CDC for all kinds of databases. Instead, it's a different format, different mechanisms, different semantics for all of those databases. But for you, the good news is you don't really have to be concerned too much about this, because Debezium, the project, deals with that. So it has CDC connectors for all databases you can see here. And then it actually has a few more, I think. So, and then the events which Debezium exposes to your consumers, they are rather abstract, rather generic. So for your event consumers, then it doesn't really matter, which database a particular event comes from. So is it from MySQL, or is it from Oracle or SQL Server? They all look the same. Events. So how do they look like? Well, in a nutshell, this is what you would get. So their structure resembles the structure of your database tables. So let's say you have a customer table, and with columns like ID, first name, last name, email. Those change events, they would have fields for each of those columns. And then, now if this is an update event, then it would have those two parts, right? So the old state, or the old image, as it's called, of a row, and also the new image for instance, for an insert, it would only be then this after state. And then there's some more metadata in those events. So, like timestamps, position in the transaction log, transaction ID, maybe the query, which triggered a specific change, the table name, all kinds of metadata you can use to reason about those events. But the key part is this actual structure which resembles your table structure. Okay, so this helps us a little bit with implementing this pipeline from Postgres to OpenSearch, right? So now we know, okay, whenever there's a change in our Postgres database, we can use Debezium, we can use log-based CDC to extract those changes. So whenever a new record is inserted or something gets updated or something gets deleted, we will have an event which describes this change. And of course the question is, well, what do we do now with those events? How can we take them and how can we put them into OpenSearch? And this is where Apache Flink will help us. So who has heard about Apache Flink? Okay, like maybe 6, 7 people. Who is using Apache Flink in production? Like nobody. Okay, we have to change that. So what is Apache Flink about? It's a platform for real-time stream processing on bounded and unbounded data streams. So what does that mean? You have all kinds of data streams. So for instance, click events from a web application, maybe IoT sensor data, or as in our case, as in our CDC case, an unbounded stream of database change events. So you have those streams of data, and now you would like to process them, you would like to reason about them. So maybe you would like just to filter them and just discard specific events. Maybe you would like to modify them, change some data formats, some timestamps and so on. So you can do processing, and then of course you also can take those events or those messages, records, and put them into sync systems. So something like, another database, maybe an S3 bucket, maybe a data warehouse. But in a nutshell, it's real-time ETL. So taking data from one place to another, putting it to another place, and optionally do some sort of processing. And I mentioned like filtering, mapping, which all are stateless operations, but you also could think about stateful operations. Something like you could join multiple streams together, or you could create aggregations, windowing queries, and so on. So that's in a nutshell Apache Flink. There could be entire talks about it, but really that's it, real-time stream processing. Now, to dive a little bit into what it offers to us is there is different layers of functionality, and they have an increasing degree of abstractness, which makes them easier to use as you go up in this model, but also they are slightly less powerful and flexible. So at the bottom, you have just your fundamental building blocks, which, for instance, provide you the means to describe events or state or event time, those kinds of things. And then you have different layers of APIs on top of that. So the most powerful one would be what's called the data stream API. So that's a Java API, which allows you to implement stream processing jobs with all the flexibility you would have in Java. So you could do pretty much everything. Next, we have what's called the table API, so that's a relational API. There's a Python-based API called PyFlink, and finally, there's Flink SQL. And Flink SQL, well, as the name says, it's a SQL-based vehicle for you to implement stream processing jobs. So you describe your stream processing logic, filtering, joining, grouping, mapping, aggregating, and so on, using SQL. And now I would argue that's the most simplest to use because, well, there's many more people who can implement something in SQL rather than, for instance, in Java. It's declarative, so you don't really have to think about optimizations that much and so on. But also it's a bit less powerful, right? So for instance, using the data stream API, you could call an external web service to enrich your change events. That's not something you could do with Flink SQL. But SQL, that's what I would like to talk about today. Okay, so how can we bring those two things together? So CDC for getting change events out of a database, Flink for stream processing. And this is what we could do in the simplest case. So we could integrate our CDC stream into Flink, into our Flink job, using a component called Flink CDC. So this just takes Debezium and makes it available as Flink native event streams. And we could just take those events which we get from our database and put them into another database, basic replication use case. But then, of course, we would, if we just were to do replication, we probably would use other tools. Very often, we would want to do things like processing this data a little bit, right? So like normalizing our date formats. Maybe there's a few columns in our tables which we don't want to expose to specific consumers, so we would like to discard them. That's something we could do. Maybe you might want to encrypt data, all those kinds of things. So, you know, basic stateless transformations. Of course, there's a variety of data things where I could put my data to. So I mentioned already databases, S3, Apache Pinot, maybe Kafka, of course, and of course also OpenSearch, which is what I would like to talk about today. And we could do multiple of those things at once, right? So once we have ingested a change event stream into Flink, we could also route this data to multiple things. Coming back to stateful transformations, so this is also something which we could do. We could join multiple streams. So let's say we have purchase order data coming in via a Kafka topic. And there's, of course, a Flink Kafka source connector. And maybe we have some reference data, like, I don't know, store IDs or product categories, something like that in a relational database. So we could ingest this reference data using Flink CDC, and then we could enrich those events which come in via the Kafka topic with those CDC-based events. All right, so let's talk a little bit how we can use those tools, Debezium, Flink, change data capture, stream processing, for implementing this data pipeline from Postgres to OpenSearch. And this is what I would like to, well, I'm not building it from scratch, but I'm showing you how to do it. So we have, you know, sort of a microservices architecture, maybe two microservices. One has a Postgres database, and there lives our purchase order data and order lines data. So that's two tables in this database, in this Postgres database. And for each of those tables, you have one of those event streams. So we have a purchase order stream and an order lines stream. Then another microservice manages our shipments. So we get a shipments stream from that one. And now we would like to essentially join those three streams together. So we join our two tables from the Postgres database with the data from the shipment service. Why would I like to do this? Well, in a system, in a document store like OpenSearch or Elasticsearch, I typically cannot do query time joins, like in a database. Instead, I need to denormalize this data and essentially put all the data I would like to query in a given context. I need to put this into a single index, and then I can search on that. I cannot do query time joins. So this is what this real-time data pipeline will be about. Okay. So let me check the time first of all. Yes, this looks good. So then let's see. What do we have? I have a few things which I have running here, and I'm using Compose to launch this up. And while this is starting, I also can show you a little bit what's going on there in my Compose file. So let's see, Docker Compose. So I have, you know, my Postgres database, maybe a bit bigger. I have my MySQL database, then I have those components, Job Manager and Task Manager, so they are my Flink service. I'm not diving in too much into the details there, but that's Flink, essentially also the SQL client. And then I have two nodes of an OpenSearch cluster. So this is where I will take the data. So I have all those things there. Now, let me get a shell first of all for Postgres. So that's the one I have here. And I just can take a look into my Postgres database. So let's say select star from purchase orders and, you know, basic purchase orders. So I have those there. Now what I would like to do is I would like to ingest the data from this table into Apache Flink. And to do that, I create what's, in my opinion, a bit confusingly also called a table, but it's not really a table because it's more, or let's say it's a continuously updated table. So let me create this. And you know, it has the same schema as our Postgres table, so order date, purchase ID, and so on. But then I have all those connector options there. So in this case, it says, you know, this table is backed by the Postgres CDC connector, specific credentials, hostname, and so on. And it's reflecting the contents of this purchase orders table in the inventory schema. So let me create this. And now what happens is this runs now the log-based CDC connector under the hood. And whenever there's a change in the Postgres table, it will be reflected in Flink. So what I can do is I can take a look at this table in Flink now. Purchase orders, okay. And I see the same data I see above, I also see it here down in Flink. And to make the case that this is not a static data representation, let me just do an insert. So I just insert another record into this Postgres table, and very shortly thereafter I see, okay, it also got inserted here, it's visible here, right? And the same as if I were to do updates or deletes on the source side, the data representation in Flink would be exactly the same. So that's continuously updated as my data changes in Postgres. Okay, so I have that. Now let's think a little bit about joining data. So I want to do a join. How would I do that? Well, I just run a join query, and now in this case I already have set up this shipments table or stream, so I can join against it. So that's coming from my SQL. And then I can, take a look at this data, which now contains my shipment data. So that's pretty neat. And again, this also gets continuously updated if the data either changes in MySQL for shipments or for purchase orders in Postgres. Okay. So we have the first half of this data pipeline, right? So we can react to changes in real time, and we can take a look in the Flink SQL client. But of course, we would like to take this data into our OpenSearch index. And this is what I'm going to do next. So now I create another table, and this table contains now, well, it has the structure of this join, so like all the columns. And now in this case, it's using this OpenSearch connector, and in particular, it's a sync connector, which means whenever we do an insert into this table here on Flink, then this will be written into the OpenSearch index. And again, same for updates and deletes. So let me do this. And then, of course, just creating this table is not enough. I also need to connect those two tables. And this is exactly what I then also do using Flink SQL. So I create this job here, and I just say I would like to select all the data from my purchase orders joined with shipments, and I would like to index that into this table. And now this gets deployed as a job onto my Flink cluster, which I have running here. And again, whenever now there's data changes on either source table, this join will be recomputed, and the particular record will be sent to the search index. And to make the case that the data is actually there, let me just take a brief look at it. So I'm just using the REST API of my OpenSearch index. And this is, for instance, now how one of those purchase orders looks like. And it also has some shipment data. So, and of course, now I could use much more of the functionality in OpenSearch, right? I could build dashboards, I could do proximity search, and so on. But here is my data. Okay, cool. So let me see what else is there. Right. Let me briefly go back to my slides, because so far we have joined two of those tables, right? Orders with shipments. But as I mentioned, I have another table, order lines, in my Postgres database. And the thing there is, well, this is a one-to-n relationship between purchase orders and order lines. So one purchase order can have multiple lines. So this is how it could look like. Those three lines, they all reference the same purchase order. Whereas in my search index, I mentioned I cannot do query time joins. I need to denormalize this data. So I would like to have a representation which looks like here on the right-hand side. So I would like to have a document which describes an entire purchase order, and then its lines are embedded as a JSON array. And now the question is, how do I create this structure? And this essentially, this is something which I can do with a function. So I take essentially data from the many side of this join and emit this data as an array for each purchase order. Now the thing is, there is no function in Flink as of today which would do this in a type-safe way. So this function array egg, it doesn't exist in Flink as is, maybe at some point. But we can add our own custom functions into Flink, called user-defined functions. And this is how this could look like, not diving too much into the implementation details, but essentially what happens here is this keeps track of the state of one of those join results. So whenever like a row gets added, I need to add this into my state. When a row gets removed, I need to remove it. And this is essentially what happens here. Now let's see how we can use this. And for that, I'm going back to my demo environment. And first, I would like to create this third table, order lines. So I have not done this yet. So again, this is using the Postgres CDC connector. It's now ingesting changes from this order lines table, right? So let's create that. And let me, I have already registered this function, so I need to declare this in Flink. I have already done this. Now I want to create this final output table, which now looks like this. So this represents now the entire join width, right, of purchase orders, order lines, and shipments. And as you see, all this is fully typed. So my order lines, this is an array of row data. So this is a strongly typed structure. Each of those rows, has proper types like int and doubled and string and so on. And it's an array of those lines. And again, this is now backed by the OpenSearch connector, so it writes to OpenSearch. So let's create that. And I also need to do this insert job again. And now I would first of all continue the cancel the one which runs there before. Let me close this. So that's the one I had submitted before. I would like to cancel this. And by the way, this is the Flink web UI, so I can use this to examine my Flink cluster. And then I can do the new one. So let's take that. And this is now calling this array UDF, right, which I've shown you before. So let's go to our Flink cluster again. So we should see now, okay, there's this new job running. This is fine. We can, for instance, also take a look at its topology. There's some back pressure here. Shouldn't concern it too much. But let's take a look at the data again. So this writes to this index there. And now I see exactly this denormalized event data, right? So one document for this purchase order, and it has this array of order lines. Okay, that's pretty neat. And again, just to make the case this actually is working, so let me insert another order line for purchase order 10001, so a third order line. And if I retrieve that data from the search index now, then I see, okay, I have now also 3 lines, right? And the same would, again, if I were to update an order line or if I were to remove one, it would be incrementally updated here. And all this with a very low timely latency. All right. And then, of course, I could go now to my OpenSearch index. I could build dashboards around it. I could do analytics there, all kinds of goodness. Okay, good. So let me go back to my slides. There you go. All right. And yes, I realize with this user-defined function stuff, it's probably a lot and a lot to take in. And I have created a video which shows you how to implement this. So if you take this QR code, it will take you to the Decodable YouTube channel, and then you can find out how to implement this kind of UDF, how to register it, and it allows you to find out exactly how to do all this. And as I mentioned, well, once we have ingested data in real time into a stream processing system such as Flink, the sky really is the limit. We can do all kinds of use cases on those data streams. So for instance, let's say we would like to do some sort of fraud detection. So maybe whenever a shipment address changes of a purchase order, we would like to notify some employee and they can verify whether this new address exists or something. So this is a second use case which we can implement on top of those existing streams, because in that case I would just deploy another job which then would just take changes from the shipment stream or events from the shipment stream, and it would filter them whenever there has been a change to the shipment address, and maybe I would take this data and send it into a Kafka topic, and then I could have some application which listens to this Kafka topic, and then we could react to those address changes. All right, so what have we seen? Well, I hope I could show you, okay, this is a very powerful and very also reliable way for implementing such a data pipeline from a system. And of course, it's just an example, right, from a system like Postgres to OpenSearch. So instead of those dual writes, which we saw initially, like trying to update those resources all at once and somehow trying to make sure they stay consistent, which we really cannot because we just don't have shared transactions there. Well, with this sort of pipeline, which is based on a transaction log of the database and then uses asynchronously execute stream processing, we can do all this in a reliable way. Tools I mentioned, well, Debezium again for change data capture, support for a variety of databases, Apache Flink for stream processing, and what I'm excited about really is about the combination of those tools, using them together, right? So in the example today, we saw a simple data replication use case. I would say taking data from a database into search index, but then of course there are so many more things we could do, right? We could do aggregations. I don't know. Maybe we are curious to have a dashboard which has the revenue per purchase order category in time windows. So this is something which we could express using Flink SQL, push the data, I don't know, into Kafka topic maybe, or maybe even via WebSockets to a browser, and then we could have real-time analytics use cases. We saw denormalization, and there's many, many more things. Now, if you would like to do all this in a production environment, there's quite a few things to consider, right? So I probably wouldn't do it like with Docker Compose on your laptop. Rather, I don't know, you might want to run it on Kubernetes, and or maybe in the cloud, of course. And of course, now there's so many questions to answer around it, right? So how do you just provision your resources, make sure they scale up and down as your workload changes? How do you keep this observable? So maybe you have some delay in this sort of pipeline and actually your changes don't flow into OpenSearch with the SLA you have. So how do you find out about this? Then if you have things like joins or aggregations, they are stateful. This means Flink needs to keep state, typically in a system called RocksDB, like an in-memory key-value store. So how do you persist this and how do you make sure you don't lose this state? How do you go about schema changes? So maybe the schemas of your source tables changes. So how do you reason about it? What do you do with it? Then what's your overall developer experience? So you wouldn't use the Flink SQL client and issue queries there. Rather, you would like to put those jobs into revision control and deploy them automatically when they have been changed. All this kind of stuff. So you would like to have some sort of CI/CD flow. And of course also security, right? So maybe you are a large organization, you don't want everybody in your team to be able to access all of your jobs you have, so you would like to have some sort of role-based access control. And this is my long-winded way of saying, probably you would like to use a platform which runs all this for you, and I happen to know and to work for a vendor which can help you with that. The last thought I would like to send you home with is this. So we spoke a lot about events. Coming from a database, but also from click streams or whatever. And an interesting thought, in my opinion, is, well, the value of individual events, it's very high initially. So changes which describe a particular purchase order, they are very valuable right now. So for instance, we would like to take those events into our search index really quickly, right? Because we don't want to update our search index tomorrow. We would like to have it in sync like within seconds. So the value of individual events, it's very high initially, and then it degrades over time. So if you look at, I don't know, clickstream events from last year, you probably don't care at this point, individual events. Whereas the value of aggregated events, it grows over time. So if you look at all the change events for all your purchase orders, this becomes very interesting to look at them all at once. For instance, you might find patterns like, I don't know, this customer who ordered this particular product, they are also likely to order another particular product. So the value of aggregated events, this grows over time. And those tools like Debezium and Flink, they help us to take value and gain insights into data on either side of this chart. Few resources. So of course, all those projects are on Twitter or X, I guess. They have obviously a website. And then all the source code for this example, which I showed you today, you can find it in the decodable examples repo. So this QR code will take you to this examples repo, and then you can play around with all this by yourself. And I think with that I'm done, and let's see, yes, there's time for questions. So if there's any questions, now would be a good time. Please. What is what? What is the cost of streaming? You mean in a dollar amount or like a mental burden or? Do you use what? Do you use connection? Are you pulling for the streaming for Debezium for changes? Right. So there's a cost for it. Okay, so I hope I get it. So is there like, let's say, an impact if I set up something like Debezium onto my source database, and I don't know, has it a performance impact on the database, right? Okay. No, typically not, because tailing this transaction log, it's a cheap operation, I would say, and people use it with, I don't know, hundreds of databases. I'm aware of really large-scale data deployments. So it's not something you would have to be concerned about, and in particular because it's not what we would call query-based CDC, which is then actually querying your actual tables and scanning all the data and like in a loop like all the time, whereas here this is more push-based. So it's I wouldn't be concerned about it. Yes, please.
I have a question about how can we handle the database table changes, DDL changes?
Right, schema changes.
In the presentation, it's only about insert and delete like queries, but Debezium is not being triggered by the DDL changes. And how can we configure the pipeline?
Right. Oh, okay, so the question is how can we handle schema changes? And so if our source tables get new columns or things like that, right? And the question is, what I would have to ask you is, what do you want to happen in this case? So, for instance, in a replication-like use case like this, let's say a column gets added to a table. Probably it makes sense then to also add this as a field into your search index in this case, right? Or add it as a column in Snowflake. Right, yes, that's right, that's what I'm trying to say. So essentially, yeah, you would have to update this Flink pipeline then as well, right? So if you have like a new column, then you would have to also add this new column to your SQL pipeline and to those tables in Flink. Now, oftentimes, and the question now is, maybe you would like to shield your consumers from those changes. So maybe you rename a column in your source database, and maybe you don't want to have the data in the search index to also be impacted by that. Maybe you would like to keep the old name there. And this is also something which you could do, because essentially you could then have a Flink SQL pipeline which, depending on whether it gets an old or new event, it could take either value and propagate it into like always using the old name. So I think the answer is it depends a little bit on what you want, but generally with Flink SQL you have the means to either abstract your consumers or to propagate that change as well. Does that help? Perfect. Any other questions? If not, thank you so much for attending. I will also be available out of the hallway so we can talk more, and have a great conference. Thank you so much.